Hello everyone, I'm going to make a presentation about biodegradable nanocomposite of polycaprolactone with cellulose nanocrystals. Polycaprolactone is a biodegradable polymer that is widely utilized for environmentally sustainable packaging films. Among various biodegradable polymers, PCl is a hydrophobic semicrystalline linear aliphatic polyester with a low melting point, approximately 60 degrees Celsius, which allows easy processing. However, deficient mechanical properties of PCl constrict its applicable field. In this study, PCl was synthesized via in situ polymerization using cellulose nanocrystals to improve the mechanical limitations. To maximize the dispersion state of hydrophilic CNC within hydrophobic PCl, the solvent exchange method was used and was dispersed in caprolactone for ring opening polymerization. With such method, a homogeneously dispersed nanocomposite was obtained that showed improved mechanical properties with a trace amount of CNC, broadening the applicable potential. Before in situ polymerization of PCl with CNC, we prepared pre-dispersed CNC in the caprolactam monomer using solvent exchange method. First of all, CNC was dispersed in the water and then the water was exchanged to acetone. After that, the CNC was separated by centrifugation. Separated CNC was dispersed in caprolactone by magnetic stirring. This pre-dispersed CNC solution, octadecanol and tin catalyst were added into a 3-neck round flask-equipped mechanical stirrer. The mixture was heated to 160 degrees Celsius and stirred when completely melted under a nitrogen atmosphere. The final product was removed from the reactor when it reached maximum torque and the product was dried for overnight. To synthesize solution-blended PCl-CNC nanocomposites, the crushed homo-PCl and CNC were added in chloroform and stirred at 25 degrees Celsius for an hour. The solution was sonicated for 10 minutes using a bath sonicator. The homogeneous solution was dried and crushed under liquid nitrogen for 10 seconds. To investigate nanofiller effects, we synthesized PCl and nanocomposites with various contents of CNCs by in situ polymerization. And you can see the tensile and tear test results in the figure 1. Tensile and tear properties increased as the CNC content increases. However, over 0.58% of CNC, there was no reinforcement effect as a nanofiller. When 0.38% of CNC was applied, tensile and tear toughness was the best, which is almost 30% increased than the neat PCl. The stiff to tough tuning trend of PCl series was verified by observing the fracture morphologies of the tensile tested specimens of stiff PCl and tough PCl CNC nanocomposite. The remarkable grain structures on the relatively smooth fracture surface of PCl reveals that cracks propagate along crystal grain boundaries during deformation. Meanwhile, PCl CNC nanocomposite exhibited an uneven and rough fractured surface accompanied by crazing phenomenon. The evolution of microfibrils through crazing promotes ductile deformation because they act as bridges that absorb external stress. As a result, crack propagation and fracturing are delayed during the tensile testing of the nanocomposite. We already proved CNC's reinforcement effect as a nanofiller. But if we can maximize the dispersion state of CNC before in situ polymerization, the mechanical performance would be improved more. Herein, we tried CNC dispersion solvent exchange method using water and acetone. In the non-solvent exchange method, CNC was dispersed in caprolactone directly, as you can see the dispersion state in figure 3a. Generally, CNC has good dispersibility in water, and acetone is amphiphilic and is well dispersed in both water and organic solvents. Water, which is a dispersion solvent of CNC, is first replaced with acetone to secure CNC dispersion stability. Through this process, CNC dispersed in acetone can be obtained. Acetone, which is CNC dispersion solvent, can be dispersed without phase separation by substituting another organic solvent. With this method, CNC dispersibility much improved, as you can see the figure 3C. Also, CNC particle size in the dispersion solution decreased through solvent exchange method in the figure 3B and D. As a result, we can see the tensile toughness increased in the figure 4. During the in situ polymerization PCL with CNC, we expected the CNC nanofiller interacts more with the polymer matrix through chemical modification of CNC surface than ex situ approach. In the figure 5, we can see the toughening effect is much more noticeable in the in situ method than that in the post-blending method, probably because the higher dispersibility maximizes the toughening effect of CNCs. To investigate the CNC surface modification of PCL CNC nanocomposites, excessive CNC, which is 5% was in situ polymerized to PCL CNC nanocomposite and solution blended with the homopolymer in chloroform. And then used CNCs were separated out from the polymer part. The chemical structure of the used CNC was identified by FTIR, and you can see the result in the figure 6. High molecular weight polymer portion of solution blended CNC was easily removed by centrifugation. But the in situ polymerized CNC showed many polymer fingerprints, indicating a covalent linkage with nanofillers. This means the carbonation of hydroxyl groups on the CNC surface occurred during in situ polymerization. Since I don't have enough time, I'll skip the conclusion part, but you can see this part through this page. And thank you for listening my presentation.